This is the foundational module in the book Problem Solving Guide for Mechanics and Thermodynamics. Here we cover unit conversions and trigonometry with vectors. These are prerequisites. For this course, humans use a variety of standards to measure things: length, inches, feet, miles, fathoms, furlongs, light years, durations of time, seconds, hours, weeks, fortnights, years, centuries. When values are expressed in different units, it is sometimes difficult to compare them. It's not obvious whether 30 meters per second is faster than 60 miles an hour. It would be easy to compare them if they were expressed in the same system of units. So the key to understanding how to convert the units of a value is that you do not change the value. You don't want to change the speed, you only change the units in which the speed is expressed. So 12 inches is the same as 1 foot. The length is the same, different units. The way to convert the units of a value without changing the value is to multiply that value by 1. When you multiply something by 1, you don't change its value. So let's convert the speed, the units of the speed, 30 meters per second, to miles per hour, so we can determine if it's faster than 60 miles an hour. So we start by writing the speed, 30 meters per second, and then we multiply by 1 until we get the units we want. So we want to cancel out the seconds, which is in the denominator over here, so we put it on the top over here. So now we have 1800 meters per minute. That's the same speed as 30 meters a second. The fraction in parentheses is equal to 1. 60 seconds is the same as 1 minute. When the numerator is the same as the denominator, the fraction is equal to 1. So let's do it again. We have minutes per hour. There are 60 minutes in 1 hour. The minutes units cancel, the second units cancel. We now have meters per hour, which is 108,000 meters per hour. Now, finally, we're going to go from meters to miles. There's 1609 meters in 1 mile. We put that in the bottom. The meters cancel. We get miles per hour, and it's 67.1. So 30 meters per second is faster than 60 miles an hour. One type of conversion in which students have had trouble with over the years is when the units are raised to a power. So if it's an area or a volume. In the thermodynamics section of this book, we're going to be working with the equation PV is equal to nRT. R, the gas constant, is usually expressed in SI units, which is meters. There's a meters in there. And the variable V is volume. Sometimes the volume is expressed in cc's or liters, and we have to convert that to cubic meters. So there's a problem that says we have 100 cc's of helium. We want to plug it into the equation. We need to convert it to cubic meters. So we start with the value itself, 100 cubic centimeters. There's 100 centimeters in a meter, so it's a common mistake to say that 100 cc's is the same as 1 cubic meter. But when we do it, you'll see that it is not, and hopefully you'll understand why not. So here's the volume, 100 cc's, and we're going to multiply by 1. This is centimeters times centimeters times centimeters. This is 1 centimeters. So now, when we do it, the 100s cancel, so we get 1 centimeter squared meter. And there's nothing wrong with that unit of volume. It's a fine unit of volume. 1 centimeter by 1 centimeter by a meter long. It's a square tube, like that. It's got 1 centimeter by 1 centimeter, and it's a meter long. And it's got 100 cc's. There's 100 cubic centimeters in there. Let's convert one more unit. So now we have 2 ones here. 100 divided by 100 divided by 100 is 0.01, and it gives you a mixed unit of meters squared centimeters. So what's a meter squared centimeter? What does that look like? It's a tile that's 1 meter by 1 meter, and it's got a height of 1 centimeter. Something like this. To get to cubic meters, we have to convert all 3 of the centimeter units to meters. So now we have centimeters cubed in the top, and we have centimeters cubed in the bottom, and we have meters cubed in the top. And if we multiply all this out, we get 1/10,000th, 0.0001. 100 cc's is 1/10,000th of a cubic meter. That's surprising to most. But let's look at a picture. Here is 100 cc's. It's 1 centimeter by 1 centimeter by 100. And you can put 100 of these right down this edge. And there's 100 of them will go across. So you need 100 by 100 of these tubes to fill out this cubic meter. 100 times 100 is 10,000. So this is 1/10,000th of the volume of a cubic meter. This type of conversion causes problems for everybody. Here is a documentary about Ethiopian wolves.
The pack's hunting ground is about 8 square kilometers of mountain top.
So, David Attenborough says 8 square kilometers. This text says 5 square miles. Those are not the same. That is a bad conversion. Let's see why. He says, the narrator, 8 square kilometers. The subtitle says 5 square miles. 5 square miles is a lot bigger than 8 square kilometers. So let's compare them with a picture. There is 8 square kilometers, and there is 5 square miles. So let's do the conversion correctly. We start with the value itself. David Attenborough's right. It's 8 square kilometers. We multiply by 1 twice, and we get 3 square miles. So we have square miles in the top, and the 2 kilometer units cancel, and we get square miles. The person who did the conversion only converted one of the units and got 8. 8 got 5. 8 divided by 1.61 is about 5. Another prerequisite for the course is mastering the trigonometry needed to get the components of a vector and the vector from its components. So let's go over a few of these. A child is pulling a sled with the rope. Pulling up like that. The rope makes an angle of 40 degrees with the horizontal. The tension in the rope is 50 newtons. We want the horizontal component of the force on the sled because that's the thing that's pulling the sled, is the horizontal component. And this is exactly what trigonometric functions were designed to do. So let's start by sketching the vector. There it is, 50 newtons, 40 degrees above the horizontal. We want to know the horizontal and the vertical component. This is the part that's pulling, this is lifting up. Both t sub x and t sub y, the x and the y components of the vector, are some fraction of the hypotenuse. And these fractions are the trigonometric functions, cosine and sine, respectively. Cosine and sine are fractions. They are the fraction the side is of the hypotenuse. That's all sine and cosines are. They're just tables. Tables of values. The definition of the cosine is adjacent over hypotenuse. If you forget that, ask me. I'll tell you. You don't have to remember that. The angle here is 40 degrees. So cosine of 40 degrees is 0.776. So this means if there's a 40-degree angle, the adjacent side is 76.6% of the hypotenuse. That's what cosine means. And we can write it. Cosine 40, adjacent over hypotenuse. The adjacent side is t sub x. The hypotenuse is 50 newtons. And we can solve this equation for t sub x. And we get 38.3 newtons. So that's the horizontal component. Let's get the sine. Let's get the other side, the opposite side. Sine is opposite over hypotenuse, and that's 0.643. So if there's a 40-degree angle, the side opposite it is 64.3% of the hypotenuse. The opposite side is t sub y. The hypotenuse is 50. We can solve this equation. We get 32.1 newtons for t sub y. So now let's go the other way. We have the components. We want to get a vector. We want to get the magnitude of the vector and the direction of the vector. So we have an arrow going through the air. The vertical component of the velocity is plus 20. The horizontal component is plus 30. So here's the vector diagram. We want to know the speed. How fast is this arrow going? It's going 30 meters per second this way, 20 meters per second this way. It's heading in this direction. And what's the speed? And what's the direction? To get the speed, we just use the Pythagorean theorem. It's the hypotenuse. The speed's the hypotenuse. So let's plug in the numbers. And we get 36.1 meters per second for the speed. There it is, 30 meters per second this way, 20 meters per second this way, 36.1 meters per second is the speed. Now we want to get this angle. We can get it from the tangent function. Tangent is opposite, which is 20 meters per second. The adjacent is 30 meters per second. We get tangent theta is 2/3. To solve this, we take the inverse tangent or arctangent of both sides, and we get theta is arctangent of 2/3. The angle whose tangent is 2/3. If we have a calculator, we can get 33.7 degrees. So the arrow is moving 36.1 meters per second at 33.7 degrees above the positive horizontal axis. So these manipulations, going from converting the units in which a value is expressed, getting the components of a vector, and then getting the magnitude and direction of a vector from its components, these are prerequisites for the course. You have to know this coming in. There's a test on Blackboard, the foundational module exam. If this exam is not trivial for you, we recommend developing this mastery before the semester starts. There's a lot of problems in the book. We have a foundational module in the book. Do those problems. And if you can't get them, you probably should delay taking 131 until the spring semester. Get to work.